Now let's talk about Taylor series. In the past I used the phrase Taylor polynomial. What's the difference between these things? Well, when I say Taylor polynomial, that only goes up to a finite degree. Linear, quadratic, cubic, 30th degree Taylor polynomial approximation. Okay, those are approximations of a function. A series goes on forever. So when we say Taylor series, we're thinking of a series that goes on forever, and it can be viewed as a representation of the function f of x, at least where the series is valid. And we're going to, in a minute, state some common Taylor series, but actually to enable us to do an example, we're going to go on a little meandering sidebar and talk about complex numbers. You may have heard of these before, but in case you haven't, complex numbers are numbers of the form a plus ib, where a and b are real numbers, and I squared is -1. Or saying that differently, you can think of I as being the square root of -1. So complex numbers work according to pretty much the rules of algebra that make sense. So if z1 is a complex number 3 minus 2i, for z1, we just multiply everything by 4. It's 12 minus 8i. If z2 is 2 plus 5i, and we want to add z1 and z2, we add the real parts together, and we add the imaginary parts together. That's the parts without i's are the real part, the parts with i's are the imaginary parts. So 3 plus 2 is 5, and -2 plus 5i is 3i. So z1 plus z2 is 5 plus 3i. You can also multiply. So let's say we take z1 and we multiply by I. That would be 3i minus 2i squared, but I squared is -1, so that would be 3i plus 2. So one last thing to know about complex numbers is that there's a really cool and important and beautiful formula called Euler's formula that says e to the ix. So you kind of have like something involving this crazy number I in the exponent is equal to cosine of x plus I times the sine of x. So it relates an exponential to trigonometric functions, really important, and we're going to see that this is true with Taylor series. So what are some good Taylor series to know? You can certainly derive these using Taylor's formula, but there are also ones that it's just really convenient to know off the top of your head. So sine x follows this pattern. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So the things to note are that it starts positive and these signs alternate, and that all the powers of x are odd. And that's because sine is an odd function. Like if you ever learned about even and odd functions, odd function means sine of -x is negative sine of x. And so all the powers of x have to be odd. Similarly, cosine of x is all even powers. So x to the 0 is 1, x squared, x to the 4th, x to the 6th, and then we alternate signs here again. And that's because cosine is an even function. That's why we can only have those even powers. Third really important function to know the Taylor series for is e to the x. That's 1 plus x squared over 2 factorial, and so on. And so just as an example, one way to show Euler's formula is with Taylor series. You can take e to the ix and just substitute. So everywhere you see an x, let's substitute ix for it. And we can do that on the right-hand side too. So the Taylor series for e to the ix should be 1 plus our x becomes ix plus our x squared becomes ix squared over 2 factorial plus ix cubed over 3 factorial, and so on. And then we'll just do a little math here. 1 plus ix. When we square the I, it gives us a -1. When we cube this I, it gives us a -I. When we take this I to the 4th power, that gives us a +1, and so on. So now what I'm going to do is collect all of the terms that have no i's, and I get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And then collect the terms that do have i's, so that's I times x minus x cubed over 3 factorial, and so on. And what you can recognize is that this thing in the first set of parentheses is just the series for cosine x from up here. This thing in this set of parentheses is just the series for sine x from up here. So therefore, using Taylor series, we've argued that e to the ix is equal to cosine x plus I sine x. And that's Euler's formula. So there's a really important question about whether Taylor series converge. I mean, it's a series, so you have to ask if it converges, and the answer is not always. And you have to do convergence tests to tell you. The only one that I really want for you to know is the ratio test. So let's see how this works. We're going to take a Taylor series, and I'm just going to tell it to you, and we're going to apply the ratio test to it. So let's take natural log of x and expand it near x equals 1. So that's taking a equals 1. We have f of x is x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3, and so on. And I'm just telling you that's the Taylor series, but you could apply Taylor's formula to get it. In general, we can write it in the form sum from n equals 1 to infinity of minus 1 to the n plus 1, that's the alternating signs, x minus 1 to the nth power, that's this term, this term, and this term, and then divided by n, that's this term and this term. Okay, so we're going to apply the ratio test. So we take the limit as n goes to infinity of the absolute value of the n plus first term. So everywhere I see an n here, I substitute n plus 1. That gives me this business. Then I'm supposed to divide by the nth term, or I can multiply by the reciprocal of the nth term. So I'm going to multiply by the reciprocal of this thing. And what we see is that since we're taking in an absolute value, these -1 terms don't matter, so we're going to ignore them. I have an n divided by an n plus 1, and I have x minus 1 to the n plus 1 divided by x minus 1 to the n. Most of those factors cancel out, and I'm just left with x minus 1. So as I take the limit as n goes to infinity of this whole thing, there's no n's in this part, and the limit as n goes to infinity of n over n plus 1 is 1, right? It's like a billion over a billion and 1. That's practically equal to 1. So when you take that limit, you get that this is equal to the absolute value of x minus 1. And you remember that what the ratio test tells you is that the series converges only when this is less than 1. So we need absolute value of x minus 1 is less than 1, which tells you that x is between 0 and 2. And this is called the interval of convergence. Outside of this range, the Taylor series does not converge. So literally, like if you were to plug in 2.1 into that series and keep taking more and more and more terms, it would not settle down to something. It would not converge. And this means you should not use it there, right? You can only use a Taylor series to describe a function inside the interval of convergence of the series. Now, just because it converges doesn't actually tell you that it converges to the right thing, right? So that's a separate question. That's going to require us analyzing the error term, which you haven't learned about. It's something we're going to postpone until later.